So let us construct an elliptic curve whose J invariant we can give at the start. So say your J invariant is not 0 or 1728, then you can define an elliptic curve whose J invariant is just J. So if you compute the J invariant of this elliptic curve, so y square is equal to x cube, and you have this fraction 3j over 1728 minus jx plus 2j over 1728 minus j. So this is your a, this entire fraction, and this is your b. So if you compute the J invariant of this elliptic curve, you will just get J. And obviously J should not be 0 or 1728. So for J equals to 0, you use this elliptic curve, you compute its J invariant, you get 0. And if you use this elliptic curve, its J invariant is 1728. So you can always construct an elliptic curve with any given J invariant. So someone gives you some J invariant, you can construct a corresponding elliptic curve via this method. So you can find this information in chapter 2 of this book, Elliptic Curves by Washington. So this is a very good book with a lot of good examples. So let us now talk about the automorphism of elliptic curves. So automorphism of an elliptic curve E is an isomorphism going from E to E, which preserves our special point. So automorphism of two isomorphic curves, you're given like this. So all the elements U which are non-zero but lie in the closure of the field. So notice there's a K bar. So you have closure. And this was our condition for isomorphism. U4A is equal to A and U6B is equal to B. So if you're given an elliptic curve like this, where A and B are both not 0, so A is not 0 and B is also not 0, then your automorphisms are just generated by plus or minus 1. There is nothing you can do. Now if your elliptic curve is given like this, that is B is 0, then your automorphism is generated by this complex number I, where I is square root of minus 1. So obviously this is generated by this relationship. So this is just 0. Now obviously if A is 0, then this relationship does not matter. So this relationship will generate the automorphisms. So your automorphisms are z over 6e generated by the sixth root of unity. So for these three curves, these are the only automorphisms which are generated. So these are easy to see, obviously, just from this relationship. So now we come to isogenies. So we have already covered a lot of isogenies, but now we are defining it. So in isogeny, again, it's a morphism from one elliptic curve to another elliptic curve. So again, I should emphasize the fact that this morphism is the same morphism we encountered in algebraic geometry. So this is nothing but an algebraic geometry morphism. So it is given by rational functions. So isogeny of two elliptic curves over K is a morphism which maps special point of E1 to special point of E2. So obviously it should preserve the group structure. So an isogeny of the form from E to E is called an endomorphism. So we have already seen the example of this right here. So two elliptic curves are isomorphic. So we have already shown this before. If there are isogenies, there is isogeny phi going from E1 to E2, and there is an opposite isogeny going from E2 to E1. And this both these are inverse of each other. So you first apply this and then you apply this, you get ID, and you also first apply say phi and then you apply var phi, you again get ID. So this is just standard inverses. So let us give two examples of isogenies, and these are actually going to be endomorphisms essentially. So first is negation map. You're going from curve E to curve E, but you're taking a point to negative of itself. So x, y, z goes to this. So obviously this fixes O because you're going to set 0, 1, 0 to 0, minus 1, 0, and so you take minus 1 common, you just get this. So this negation map is an example of isogeny, and in particular of an endomorphism. Another more complicated example is doubling a point. So you start with the elliptic curve E, which is y square, our standard form y square is equal to x cube plus ax plus b. And so if you have to add 2 points, you have to talk about the line through the 2 points, but these 2 points are the same, so we can talk about a tangent line at point P. So this tangent line at point P, the slope is given like this. So 3x square plus a by 2y, which you find out by differentiating this. So you get 2y dy is equal to 3x square plus a, and therefore you can solve for dy by dx. So implicit differentiation gives you this. So this you get by implicit differentiation. And now we are just using the formulas for the points. So here you're doubling the point, therefore you have m square minus 2x. Plug this m square in here, you get the x coordinate, and for the y coordinate again you use this formula. These formulas for this formula and this formula we have seen before. These formulas were precisely the ones which we found from the tangent chord method of adding points. So again, now you substitute in alpha x, you substitute in m. Alpha x we have already found out here, this is alpha x. You put this in here, m is this, you put this in here, you get alpha y. So this is a rational function, so therefore it does form an isogeny, because in terms of algebraic geometry you have a morphism. But in order to see whether this fixes this point O, it involves a lot more work. So first you have to have the z coordinate, so you have to homogenize it. So you will first find the z coordinate, so which we will put as 8 y cube z cube, so that we can get rid of the denominators here and here. And then again, then we will have to normalize this 3x square plus a, so that we can show that this holds. And it's kind of a long and tedious calculation, but people before us have already done it, so therefore we can take it on faith, or you can do it as an exercise, that this will also preserve point O. So there are two examples of endomorphisms which we have discussed, and from here we can go further. So once you have 2p, then you can add another point to it to get 3p. Now this formula you may not be able to use, because 2p might not be able to equal to p, so you have to use the standard results from the addition of 2 points. So you can get 3p and so on. So you can get a general formulation of endomorphism from p going to mp. So you take the point and add it to itself m times. So this will also give you an endomorphism, because you will get rational functions in x coordinate and y coordinates. You keep on adding rational functions, you will keep on getting rational functions. So this is also an isogeny, and since we are going from the elliptic curve to itself, it is also an endomorphism.